The second problem I worked on in my thesis is the prop machine, which is a way to de-randomize a random walk. So if we look at this picture that we've all seen before, this is just a random walk. I'm starting with 10 chips at the origin, just the number 10 was chosen arbitrarily. And at each time I'm writing down the expected number of chips that will be at each position if we just follow a simple random walk. So okay, no news there. But in the prop machine we don't want to use numbers that are not integers. We just want, this is not going to be really an expected value, but we are actually going to be sending this number of chips to each side, and we can't cut any chips in half. So when there are odd numbers, there is something that we need to do to decide which side is going to get 3 chips and which one is going to get 2. The way that we decide that is that each position keeps an arrow that points to the direction that's going to get more chips. So in this example I'm starting all of the arrows pointing to the left, but that doesn't make any difference. It's just to make it simpler. So here the origin started pointing to the left, and on the next time it's still pointing to the left because the number there was even. But this position here has 5 chips, so 3 go here, 2 go there, and the arrow flips, so that on the next time the other side can be favored. So we keep doing that for a couple of more steps, and it looks like this. You can see that some places have different numbers in the 2 pictures, right? So that 2.5 is here a 3, which is a difference of a half. From here to here we have a difference of 0.75. And the interesting question is, can this difference be as large as we want? I mean, I picked an initial position which was just 10 chips at the origin, but maybe I could have used 1,000,000 chips scattered in different positions in such a nasty way as to make this difference bigger at some point. And well, for the simple random walk with 50-50 chance of going left or right by 1 unit, then it's already known that this difference can only be at most something like 2.3. So it's bounded by a constant. And what I want to do now is I want to look at different random walks other than just the simple one that we've been looking at. Is the first one, where you're allowed to go 1 step to the left and 1 step to the right. I want to be able to do different things than that. So for example, in this one, I can either go 1 step to the left or 2 steps to the right. But I still want to keep the walk with 0 drift. So whatever steps I choose, in this case, for example, the probability of going to the left has to be 2/3 and the probability of going to the right has to be 1/3, so that the drift is still 0. And I can also use a bigger number of steps than just 2. So for example, here we have a walk with 3 possible steps, 1, -2, and -5. And here we have another one with 1, -1, and -2. The difference that we can see between these 2 pictures is that the first one is periodic and the second one is aperiodic, which means that for the first one, each position only has certain times where a chip can actually get there, while the second one, after enough time has gone by initially, then each position can be filled with chips at all times. We're actually going to be concentrating on the second kind of walks, the aperiodic ones, but the result that we're going to get is the same. It would only change by a constant, so that doesn't really make much difference. So the result is this. The result is that the difference between 2 numbers, which I'm going to explain, is bounded by a constant. So what these numbers are is exactly these numbers. One of them is the expected number of chips in a position, and the other is the actual number of chips that the prop machine puts there. So E of 0t is the expected number of chips at the origin at time t, and F of 0t is the actual numbers of chips at the origin that the prop machine puts there after time t. And I'm just considering the origin because all points are the same, right? Since the initial configuration is arbitrary, if I want to look at another point that is not the origin, I can just shift everybody in the beginning. So, and this constant is really not going to depend on some things that we might think it depends on. So it does depend on what the walk is. So the walk with 1 and -1, like I said, the constant is like 2.3. The walk with -1 and 2 might have a different constant, which I don't really know the numbers, but it can be different. And it also depends on the probabilities, because when you have more than 2 steps, then you get to make choices of what the probabilities of each step are. But the constant does not depend on the initial positions and the number of chips that you initially have, where they are initially. It doesn't depend on how much time has passed. So that's a very interesting constant because it doesn't depend on any of these things.